Sir, welcome, sir. Sir, check it the audio presentation if you possible, sir. Is everything for your side is yes, sir? Sorry, are you hearing, sir? Audible my voice,
Yeah,
sir?
I can hear.
Okay,
Yes,
sir.
yes,
Okay, sir.
yes.
Just I check it, sir.
Yeah, no problem.
Okay, sir.
And I am audible. I am audible clearly.
Sir, audible is clear, sir.
Okay.
Okay. Sir, 5 minutes is there, sir. 2 o'clock. Few minutes. You wait, sir.
Yeah, no problem. No
Okay, sir.
problem. No problem. We'll wait.
கரெக்டாக 2 o'clockனா ஸ்டார்ட் பண்ணிக்கலாம் ஓகேங்களா ஓகே ஸ்டார்ட் பண்ணிக்கலாங்களா நான் 2 o'clock ஆகலைங்களா என்னாச்சுப்பா 1 நிமிஷம் ஓகே 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 வெல்கம் டு faculty scientists, students, and research scholar. On behalf of Organizing Secretary of and Principal Investigator, RUSA Skill Development Certificate course, Advances in Data-Driven Statistical Application and Computation Techniques. The project is sponsored from Government of India, M.Tech, and Tamil Nadu, Government of Tamil Nadu, and also the authority of University Authority of most respected Vice Chancellor, respected Registrar, and Professor and Head Department of Statistics, Bharathiar University, Coimbatore. The program duration, skill development duration, February 12 to February 21st, 2021. Today, they on 6th day. Today, special address Dr. ADDSACT, Associate Professor, Department of Statistics and Applied Mathematics, Central University, Tamil Nadu, Thiruvarur. Sir, MSc and PhD in Statistics from Shivaji University, Kuala Lumpur. Sir has got CSR net scorecard. Sir's professional experience, Assistant Professor 2019 to 2010, 2009 to 2010, Department of Statistics, North Maharashtra University. Assistant Professor December 2010 to December 2019, Department of Statistics, Shivaji University. Associate Professor December 2019 to still date, Department of Statistics, Central University, Thiruvarur. Sir is the associate with the postdoctoral fellow, Department of Biostatistics and Epidemiology, Augusta University, States, USA. Sir, administrative responsibility held coordinator, postgraduate diploma in actuarial science, Shivaji University. Coordinator, MS, MPhil, PhD coursework, Shivaji University, Colombo. Task Force Committee Member, International Office Cell, Shivaji University. Sir, research interest, robust estimates and model selection in records, non-parametric inference. Sir is published research paper published in 15. Paper presented in conference, seminar, symposium, including 14. Invited talk in 19. The different perspective, different locations. And also, sir is ongoing project, major research project from DST SERB 2018 to 2021. Sir is several associated with task, working peoples and academic responsibility, different administrative, academic and other of extensions work. The membership of academic bodies, International Indian Statistical Association, life member ISPS, life member of Shivaji University Statistics Teachers Association and the executive body. SAR is organizer and committees of workshop, seminar, conference, committee members, organizing secretary, convener, the different role of the organizing committee of national, international workshop, different perspective of programs. This is for short CV of SAR. In case any updates, the experience of himself, SAR. Right now, this session is handed to today's special address, Dr. Deepak Maganda Sheikh, Associate Professor from Central University, Tamil Nadu. Welcome,
Thank
sir,
you.
once again.
Thank you, Dr. Gandhiya Vendhan. Thank you for a very nice brief introduction. And of course, that is all. I don't want to add anything to that. So, first of all, I would like to thank the organizers, especially Dr. Gandhiya Vendhan, for inviting me to interact with you people on this virtual dais. Uh, I and of course we all very well know that we are still in the grip of COVID-19, and we are trying to evolve out of this situation. And as a fact that earlier these programs were held offline in presence, and if COVID-19 would have been absent, the situation would have been different. I wouldn't be sitting in my house in Tiruvarur and talking to you people through the system. This is evolution of the things as like time demands, and we can see that even the methods which we are going to discuss today in the two sessions, the first one is concerned with artificial neural network and the second one is concerned with support vector machines. These two techniques or tools, or I should say skills, which you will be taking home today, these skills are actually evolved because of the need of hour. So today we shall first try to understand why we need these techniques, why they were evolved, and then we shall actually see how what these techniques are and how they can be applied in real life to solve certain problems. I can understand that you are from varied background and even at different levels, like some of you are doing your PGs, some of you are doing your UGs also, some from doctoral background, or even I could see some doctorate people, maybe some faculty members and scientists as participants in this course. So I'll try to make it general so that everybody will have something to take back from these two sessions. So let us start discussing the fact that, like, why these methods evolved. So actually there are, like, if you look at the title of the course itself, it has one very important term, and that is data driven. So there is actually an evolution in the field of statistical modeling, I should say, or data analysis in general, that people moved from the traditional methods to data driven methods, and the reasons that we shall discuss today. And then we shall see, like, why the meaning that is not the only aspect we can see. The aspect is also from the computer science approach, and I shall discuss both the approaches so that you will understand why we need to why we need to study data driven methods. So as far as statistics is concerned, statistics is actually a field which tries to explain the uncertainty in the phenomenon. This uncertainty is explained using some statistical models. And in the process of building a statistical model, we usually assume some model involving some random variables which are governing the phenomenon. And once the model is assumed, data is collected, and data is used to fit the model uh, to the meaning model is fitted to the data. And once the model is fitted, again the process moves on to check whether the model is fitting good or bad. And if the model is fitting good, then we satisfy ourselves and move ahead with the deployment of the model. But in practice, finding such model could be difficult. If the model is not fitting good, then the question comes, like, should we go for some other model? And the answer is yes, and we need to do some trial and error stuff over there. Of course, the trial and error stuff will be based on the underlying situation. Like, you need to do some exploratory data analysis, you need to figure out why the existing model couldn't fit good to the data, and so on, and accordingly you need to modify the system. But this becomes cumbersome, and many times you may not turn up with any good model which will do for your data in your hand. And in such cases, there is definitely a need of like having models which are not assumed, but rather they are justified by the data itself. So can we learn something from the data? Can we identify certain patterns from the data which can be modeled in the form of some mathematical equation or a statistical equation, and that can be used to draw conclusions or inferences about the complete system. So this actually led to the need of like data dependent procedures. Of course, in statistics, there is a separate branch which of course don't assume much or don't put much constraints on the models, and it is popularly called as non-parametric inference. But this non-parametric inference approaches also suffer certain drawbacks, and of course, I shall not say that this is a substitute for that, but I should say that this is more efficient and sometimes will give more realistic results, provided everything is set in proper order. So this was the statistical perspective for moving from the traditional methods to the data driven methods. And as far as from computer science is concerned, the computer science aspect is actually something like this. Usually why computers were designed? Computers were designed to do tasks which humans can do, but with more efficiency. So like you can see, as the computers evolved, as the computers came into our life, many tasks which could be done by people with a lot of time, a lot of manpower was required, everything was changed, and less manpower is required to do the same task with the help of computers. So computers actually started replacing human beings in several aspects. Further, there were certain tasks which only humans can do, but computers were actually not modeled or framed in that particular aspect so that they can do the task on their own. For example, identifying an organism or an object from a given picture. Like if a picture is presented, whether a computer can identify that picture, like who is there. Nowadays you might be having a feature in your Facebook. I hope everybody is accessing your Facebook account. Whenever you upload a picture, maybe like a picture in which human beings are there, human faces are there, after some time, or maybe even at that point of time itself, the Facebook will prompt you to identify the names of the faces. It will ask you to tag the faces. So basically, Facebook, what it does, it tries to check, it tries to run through the photo and identify the objects, whether the object is a human face or not. If it finds that it is a human face, it will ask us to tag that particular face. You can see a square or a rectangle around the face of a person, and accordingly you may choose to tag or not. So how this is done? This was actually done. Of course, this may be for fun in Facebook, but this is very much essential in many fields wherein images are required to be assessed, and a proper conclusion needs to be drawn. Let us remember the movie. I guess you might have watched the movie by name Pokhran. Pokhran, which was like the first nuclear test which was done by India in Rajasthan. So you can see that Pokhran test, satellites launched by US, they were actually continuously trying to capture the images of the site wherein a possible nuclear test would have been conducted, and they were trying to figure out whether there is any sign of like whether Indians are trying to perform a nuclear test or so. So satellite images can be useful. They can be used to track down like whether anything is anomalous going on and so on, provided the objects, the procedures which are happening in the image can be identified by a system itself without the help of a human being. So that human being can be eliminated. This is actually coming in the form of like artificial intelligence. You might have heard of even I should say automatic cars, which are like driver free. I mean to say driver free cars. So all these driver free cars, they are actually still being tested for their efficacy and their use in day to day life. and it is happening, the process is going on, and you will see in near future that with the help of this artificial intelligence, which the data is captured in the form of images and videos, and it is scrutinized, and accordingly decision is taken. The very excellent example is this driver-free car itself, wherein images are captured from front, from side, from back, and from every corner, so that whatever, like if there is an obstacle ahead, accordingly the speed will be regulated and so on. So how do we identify the obstacle and so on? So all these things, all these questions can be answered using certain techniques which are not falling exactly in the statistical framework or not in a mathematical framework, but you can see like they may be some data driven, or we can make computers learn and do the things. Then the question comes like how these methods were evolved, and these methods were evolved because of the understanding that like how humans do, can we have a mathematical blueprint of a human nervous system which can do the same job with the help of a computer. And this was like very a fancy thing that time. This happened in 1950s, I will say. And in 1950s, many scientists, researchers were actually trying to figure out whether whatever a human being can do, can it be done by a computer. For example, like identifying the objects in an image. Let us just keep our mind on this particular problem, identifying an object from an image. So then of course people thought that this can be done, and this actually problem was already solved by nature in the form of human being. Like, is there any a system which can identify the object on its own and separate it out given an image? And the solution of the problem is the human being itself. And you can see that there were several clues which can justify that such type of system can be produced. The first clue, you can see that the human beings are actually a very fantastic pattern recognizers. Our visual system, our own visual system now, which you are actually using to see the screen either on a laptop or on your mobile, and you can see that something is going on. Somebody is talking, others are listening, and like somebody is commenting and so on. So all these things, like even though you don't know, even though you might not have seen something, but you can still make out what is there on the screen. So our visual system is so much strong that it can identify the objects with any orientation, with any shape, and at whatever the distance it could be, and so on. You can imagine like the even, and this is actually done surprisingly, this is done within like a fraction of, like you can say, 1/10 of a second. Within 1/10 of a second one can do this, and this is really an important clue in the direction of developing such methods. The second clue is that human brain is so powerful that we can do difficult tasks with some training. For example, with some practice, I should say, rather training. With some practice, one can do that. For example, playing a piano, playing a guitar, playing any musical instrument, or even like studying physics, studying any subject you can think of, like maybe mathematics, statistics, or engineering, whatever you feel. All these
Sir,
are
sorry for
difficult.
different disturbance. Sir,
Yes.
presenting any PPT
Yeah,
or slides?
I'll present. I'll present.
Okay, sir.
This is the
Some
introductory part.
people's asking questions, sir. That is him asking, sir.
No issue, no issue. I'll
Okay.
present. I'll
Okay,
present.
carry, sir, carry.
This is the background which I have not put on the slides. Okay. So, so I was talking about like, oh, I missed the point. Yeah, the second clue, like humans can. Yeah, am I audible? Yes, am I audible?
Yes.
So
Yes,
the
sir.
second point, and the second point which was I was talking about is like humans are. Yeah, the first point. Let me go back to the first point itself. And the second, yeah, first point is done now. Second point is something about like humans can do things which are difficult to be performed, like playing a musical instrument or even studying a subject and so on. So these things can be done with practice, of course, and without practice, doing these things is a little bit difficult. And this is possible only because of the human cerebral cortex, which is like very widespread, and it is uniform, and it is having a lot of network in our human body. The third clue, which is actually very important in this field, and that is that there is no logic which is already filled in our brain, and this logic is actually going to be the key for this particular development. There is no logic in our human brain, but logic can be developed once one can teach somebody the logic. Like, say for example, you may be knowing some programming languages. Without the logic, see, you may have different programmers. Language may be known, but the logic, unless you have the logic, you cannot perform a particular task. Logic is not there in the brain, and logic needs to be taught. And it has been, of course, empirically as well as theoretically proved that humans need to be taught logic. But of course, after teaching or after learning logic, humans can do wonders. So that is the third clue which actually led to the development of these methods. And the last one is like the neural system in human body is very widespread, and it is actually something like very advanced, and you can see the network of neurons in human body is very strong, and the impulses which are carried from sensory neurons to the central nervous system and the action taken, all these things are happening within a fraction of a second. So this is actually, I should say, these are actually different clues which can definitely led many researchers to develop what is called as artificial intelligent systems. The first thing which was thought of in this particular aspect was artificial neural network. Artificial neural network is actually used for the purpose of classification and prediction. So we shall first see the problem of classification, and then we shall discuss how artificial neural network can be applied for classification purpose. I guess my screen is visible now.
Yes, sir.
Yes, sir.
Okay. So, friends, let us try to look at these examples. Actually, the first example is concerned with the field of forensic science. I know many of you may be looking or maybe viewing some crime-related serials or some movies, or even you might have read some detective stories and so on. So basically, in forensic science, or you can see in the field of crime, usually if there is a skeleton found, then the very first question which is needed to be answered is that whether the skeleton is of a male human being or a female human being. Of course, one can easily make out whether the skeleton is of a human being or not. For that, you don't need anything. But once the skeleton is found, whether it is of a male human being or a female human being, that is a difficult question to answer. And without that answer, of course, further identifying the person whose skeleton is found becomes difficult. So this basic question can be answered using some techniques called as classification techniques. So the problem is to like identify the gender using some data. Now, how this can be done? I shall just give you one detailed explanation about like how this can be done. Like one important feature of human skeleton is that bone lengths in a particular region for females and bone lengths of the same particular region of males, they differ greatly. And you can collect, like you can have data on different bones, like measurements on different bones in the pelvic region particularly, and you can build up a function which can tell, like if the function is greater than certain threshold, the the skeleton belongs to male, less than certain threshold, skeleton belongs to female, or vice versa, either of these. So this is actually like classifying a new skeleton. So once we develop such function, then the only question remains like to which gender this particular skeleton belongs. And one can do that by just putting the measurements on the bones in the pelvic region of that new skeleton into the model and get the output, accordingly label the skeleton either as male or female. So this is how one can predict. Of course, this may not be the correct gender, but this is like the most possible gender one can go with for that particular skeleton. And this is like an improved knowledge, I should say, because earlier you had zero knowledge. Now something you know, either it could be of male with so much probability or of female with so much probability, and that is definitely going to give a new direction to the investigation of the crime. Similarly, one can imagine a situation wherein a person is, or customer I should say, is visiting a bank and asking a bank manager for a loan. As a bank manager, definitely he has to identify whether the applicant is a defaulter or a non-defaulter. Defaulter is defined something like if a person is taking a loan and not repaying, such a person is called as a defaulter. Definition of defaulters can vary. Even one installment missed may treat that particular person as a defaulter. So it depends on banks to bank, like how they will term the people as defaulters. Either one EMI missed, two EMIs missed, or three successive EMIs missed, then they may say that the person is a defaulter. So definition may change, but one can just broadly say that the person who doesn't repay the loan in time is a defaulter. On the other hand, the one who is sincere, repaying the loan EMIs at time is a non-defaulter. So like before giving a loan, if a bank manager can identify or rather predict whether this new applicant will be a non-defaulter or a defaulter, accordingly for him to make a decision would be easy. But how do he do that? So what he can do is he can collect historical data, and he can develop some mathematical function in which he can put the values on certain variables like the financial status of a customer, which indicating financial status of a customer like income, liability, credit history, and so on, based on which he can assign some probability of that person being either a defaulter or a non-defaulter. And you can see if a person is identified as a defaulter, meaning if for a person to be a defaulter, if the probability is high, then definitely bank manager is not going to sanction the loan, and so on. So you can see like classification does play an important role in the field of banking as well. And this is not the only field you will see wherein classification is happening, but in many fields. Today you might have opened your mailbox, I mean to say, and you might have even saw some junk mails which are put in your either spam or junk folder. Now how does Gmail or whatever the mail service you are using does this? Automatically, see, there is no human being which is doing or scrutinizing your mails either as spam or non-spam, or junk or non-junk. Something is running behind that. What is that? Classifier. What it does, it takes the keywords from your email and checks whether such keywords are appearing in spam mails or non-spam mails. If they are appearing in spam mails, then definitely that mail will be treated as spam and it will be automatically put into your spam folder or a junk folder, so that you will not see such unnecessary emails in your inbox. So all these things are actually happening because of classification techniques. So today we are going to see classification techniques and of course regression techniques. These are some more examples. I shall not spend much time on that. Okay. So the techniques which we are going to study, they are actually falling under the broad discipline or broad category of supervised learning methods in the field of machine learning. So basically what we are going to discuss is like two different machine learning techniques. and one of which is artificial neural network, other one is support vector machine, and both are falling under the tag of supervised learning. Now, what this supervised learning is? Supervised learning is actually human learning rather from experience. It is something like human learning from experience, or you can say human learning in the presence of a teacher. Okay, such a thing is actually called as a supervised learning, meaning somebody is there to teach. For example, when you were a kid, you might have touched a hot pot, or even you might have touched a hot iron, and in that case, immediately you might have realized that you should not touch these hot surfaces, otherwise your hand will get burnt. In that case, nobody taught you to do that, but and that is actually called as unsupervised learning. If I ask you, like, if you see the background of this slide, what color is the background? You will immediately say, sir, it is white. The white background. Who told you that such type of background or such type of color should be called as white? A teacher told you, somebody told you, either your father or mother or your teacher might have told you that such a color is called as a white color. So that is actually imprinted in your mind, and that you can recall right now. If I ask you, what is the background of this slide, what color is the background of this slide, and you can immediately reproduce and say, sir, it is white. So that type of learning is actually called as supervised learning. In the field of machine learning, or the methods which we are going to study, the trainer or the teacher is actually nothing but the class label, and the learning is actually done from the characteristics of the individual, which are labeled as x1, x2, xp, and they are nothing but the attributes or the regressors or the predictors, or you can say the characteristics of the object, based on which either we shall be performing a classification task or we shall be predicting a numerical value for the response variable. Moreover, whatever the model will be learned, it will be learned in the presence of the ideal setting. That means you know the labels, or you know the numerical value, and you know the pattern in X's. You try to understand the pattern and then try to imitate that pattern when only new X comes and you don't have any Y. So you try to identify what Y could be. Y either could be a label or a numerical value. Accordingly, the prediction will be done. This I already explained. Yeah. So these are like major tasks which machine learnings do, like prediction methods. They use some variables to predict unknown or future values of other variables. And of course, descriptive methods, I should say, or description methods, which find human interpretable patterns that describe the data. But these are actually something like clustering, or you can say, broadly speaking, clustering or even association mining. There are many methods which fall under this particular category. And in case of prediction methods, which we are going to discuss now, like either you can have classification or regression procedures. And yeah, of course, these are the broad steps in doing a statistical, or rather you can say model building. Let me just quickly go through this. Already we have seen this, that one needs to understand the purpose of the project. Then once the purpose of the project is understood, then data should be obtained, and that data either could be secondary or primary or tertiary depending on the need of the project. And first thing one needs to do is, like, one needs to explore, clean and pre-process the data. This is required as far as like what techniques you are going to do or implement on your data. Accordingly, you have to clean and pre-process the data. I guess you might have seen one, meaning in the earlier class I heard that you were discussing some outliers, and outliers are actually some anomalous observations, and those anomalous observations should be treated properly. Either they can be deleted or they can be kept in the data with proper treatment. So such pre-processing one needs to do. One needs to clean. If there is some dirty observation, some noise is there, one needs to clean, and so on. So we need to reduce the data and partition it into possibly 3 sets. This is an important thing, and I shall focus on these 3 sets. One is training, validation, and testing. This is because Model is learned on the training data. Model is validated or checked, or its goodness of it is checked on the validation data, and then it is tested on the test data. So for all these things, your labels will be available. Okay, for training, labels will be available, validation labels will be available, testing labels will be available. And you can see all these three data sets, they are like mutually exclusive and exhaustive. Now, where from these data sets come? They are not provided separately. You will be getting only one data. You have to partition your data into these three sets. You need to use your one set as training, the other set as validation, and the third one as testing. I will tell you particularly in the field of model building, usually you don't go for that validation. You have only training and testing. Okay, some people even go for validation if they are not sure of the model itself. Okay, so further, like you can see like which task one needs to do, either classification or prediction or clustering, and proceed accordingly. And one needs to identify the proper technique, use the algorithm to perform task, and then interpret the results. Once the results are interpreted, then the very important step comes, that is deploying the model. That means putting it in the real use, real life use, meaning in the current scenario, how it will work. This I already explained. Fine. So what is classification? Classification, as I told you with the help of some examples, given a collection of record, one needs to do these three things. Each record contains a set of attributes. One of the attribute is the class or label. Find a model for class label as a function of values of other attributes. Relate class attribute with the rest of the attributes. Actually, till now, what I was saying is like building up a model, building up a model. In statistics, in parametric setup, you actually assume a model and proceed, while in data-driven procedures, you learn the model from the data itself. So find a model from this training set, okay, which will be actually nothing but a function of the values of other attributes. And what is the goal of this procedure? Goal of the procedure is previously unseen records should be assigned a class as accurately as possible. As in case of your skeleton example, the skeleton is not previously observed. Whatever the skeleton we are having right now, you can see the earlier skeleton were used to build up a model. New skeleton is found. New skeleton measurements are inputted in the model, and the skeleton is now classified either as a skeleton of a male human being or a female human being. Such goals are usually set in the classification procedure. Yeah. This is another example. Of course, I should not tell you so many examples. Yeah. So what are the different classification techniques? You can see the basic thing like statistical discriminant analysis, logistic regression, Bayesian classifier, nearest neighbor rule, decision tree, and cart. All these are simple basic classification techniques. Today we are going to talk about advanced techniques like artificial neural network and support vector machines. Yeah. So this we have already seen. Yeah. Once the classifier is learned, basically one needs to assess whether the classifier is good or bad. It is done using certain metrics. One of the metric is classification confusion matrix. This is actually something like counting the frequencies of correct class prediction. You can see actual class in the rows, predicted class in the columns. That means if for instance actual class is 1, this is a number given to the class label. Okay, class 1, predicted class is also 1. How many of such data observations are there out of n? So if your classifier turns out to produce like n11 number of observations, okay, out of n, which are like which are having actual class 1 and predicted also 1. So this is correct classification, so that it is shown in green color. N00 is like actual class is 0, predicted class is also 0. So the goal is actual. Whereas in this case, actual class is 1, but predicted class is 0, and something wrong has been done. And here also something wrong is done. Actual class is 0, predicted class is 1. So these two numbers actually indicate error in classification, or you can simply say misclassification, and these two numbers indicate the accuracy. Of course, these are not the only metrics. There are some other metrics which also talk about the different situations wherein one can see like how many positives are classified as positives and how many negatives out of negatives are classified as negatives, and so on. So like true positive rate, true negative rate, and false positive rate and false negative rate, and one can build upon sensitivity, specificity, and then even go for ROC curve to understand how good is your classifier. So this is something like a typical training data, and you will see that you may have like features which are like numbers or intervals, or even you can see only categories. Here you can see like mostly categories. This is an example wherein a customer enters a store and tries to buy, meaning the store is like an electronic store in which computers are kept for sale, and the store manager is interested to predict whether the person will buy a computer or not, depending on his data like age, income, student, credit rating, and so on. This buys computer is a label variable. Yes or no. Yes, you can indicate it by 1. No, you can indicate it by 0. And these are the attributes, or you can say variables, based on which one can decide whether a computer can be bought or not. So this is like you can say some evidence for this particular labels. So if a new customer comes, then if a rule is learned, and if a new customer comes, then the store manager only needs to look at the values of his features and accordingly predict whether he will buy or not, and accordingly the treatment will be given in the store. So this was like brief outline about the problem of classification, and now we shall discuss artificial neural network. Yeah. You might be wondering, like I was talking about human brain system earlier, and the reason you will find it here, because as the name suggests, we are going to study an important classifier in the field of machine learning called as artificial neural network. The word artificial itself tells us that it is something which is in real but made artificially, and that we are applying on the computers. Neural networks are naturally available in human brain, but we are constructing some artificial, or we are trying to imitate the thing in the computer system, so that we can do similar jobs which a human being can do without the help of human being. So you can see like sensory, you can see like biological neuron network. Actually, I should say that these artificial neural networks are highly motivated. I should say they are motivated through human neural network system. And for that, to understand the basics of neural network, one just quickly needs to run through like how what is the biological background of artificial neural network. You can see in human nervous system, this is a kind of a structure. Like human nervous system is actually like into two parts: white matter, gray matter. And white matter, you can see like neurons or nerve cells. Gray matter is glial cells. And you can see like the input to these neurons is through either sensory neuron, or you can say like motor neuron, or like interneuronal cells. Okay, you can see there are the, specific functions for these things. Sensory neurons, they are actually nothing but input to the nervous system. Where are they? They are usually located at the periphery, like on the skin. Okay, whatever you touch, you can just quickly do an exercise. Just touch your second arm. You can touch your right arm using left arm. What will you feel? Something is touching. Something, meaning what? Who told you that it is happening? Without even looking, you can make out that something is touching your hand. The reason is that the sensory neuron below your skin is carrying that message within a fraction of a second to your brain that something is touching your right hand, and so on. So sensory neurons, they are like input to the nervous system. Even motor neurons, they transmit control signal to muscles and glands. This is usually happening in like a reflex action. Okay, it could be voluntary or it could be involuntary. For example, you touch a hot pot. You touch purposefully a hot pot. How long you can, even you feel that you should remove the hand, you can keep it for some time. But even if you unknowingly, just imagine that if you unknowingly touch a hot pot, immediately your hand will be taken away from that hot pot. Who does this? Brain doesn't do. Your central nervous system, your spinal cord itself does this. It is called as reflex action. How it is done? Information from sensory is taken from the skin, that surface is hot. It is taken to the spinal cord. There itself it is processed, and immediate action is ordered to the motor neurons present in the muscles of arm, that arm should be removed from the hot pot immediately. So it happens in a fraction of a second. You cannot even imagine, like if you touch unknowingly anything which is hot, immediately your hand will be taken away. This is the power of like human beings, you can see. And the third one is like interneuronal cells. These are like the connecting neurons. Like one neuron is connected to the other, and they actually propagate the signals from one side to the another, and constitute by far the largest class of cells in the nervous system. You can see that this is kind of a general structure of a neuron, and whatever the neural network we are going to see, it will be based on this concept itself. Let us just try to understand how the impulse is transferred from one neuron to the other neuron using these neurons. You can see the neuronal body, or neuron or nerve cell. This is actually the figure of a nerve cell, or in simple word, neuron. And it is divided into two parts. One is like cell body, and the other one is axon. So cell body is something, this one. You can see this is the cell body. You can just call it as soma. Soma stands for body. And this is actually nucleus. And you can see these are the fibrous joints to the cell body. They are called as dendrites. And this is actually the axon hillock over here. And this is the axon. This complete part is called as, from here onwards, it is called as axon. And you can see that there is an axon terminal. This axon terminal further joins to another neuron, and even it joins to another neuron through dendrites. So dendrite of another neuron will be joining the axon terminal over here. Similarly, this dendrite will join to axon terminal of some other neuron, and such a chain of neurons is found. It's not just a chain. You can see it's not just one facet wherein the neuron can attach. You can see there are several facets, and accordingly you can have several connections, and input from all the connections will be taken together, and it will be processed in the axon hillock. So axon hillock will be like taking your entire input, and from here the input will be transferred through axon to the next system, and so on. So this is kind of a broad picture of the functional and structural unit of central nervous system. Of course, I already explained these things. Yeah, the last one I didn't do, the synapse. Synapse is actually the point of connection between neurons, or a neuron and a muscle, or a gland. And this connection is very important, because through this connection only the information or the message is passed on from one neuron to the other thing. Either they may connect it to, like if they are like motor neurons, then they may be connecting to finally to a muscle. If they are just sensory neurons, they will be connecting neurons to one another, or even they may connect to a gland also, like depending on which some secretions are to be done. So accordingly, all these things will happen. Okay, so what are these synapses? Synapses are the joint points either between two neurons, or a neuron and a muscle, or a neuron or a gland. And this joint is not like a rigid joint. The joint is facilitated through the presence of some chemical. That chemical is called as interneuronal fluid. and it is actually having a characteristic of being electrochemical. Okay, so it enhances, or rather it facilitates the electrochemical communication between neurons. And the communication, I mean, like whatever the message has to be taken, that message will be passed on as an impulse through this electrochemical communication towards the next neuron or a muscle or a gland. This is a picture like presynaptic neuron and postsynaptic neuron over here. Okay, you can see this is these are the dendrites. This is the cell body of one neuron, and these are like axon terminal, you can see, and they are getting attached to the dendrites of one neuron. Even it may happen like you can have like another neuron over here, and accordingly the network will enhance. It need not be just like 3 or 4. You can have a broader picture. So what happens exactly is like dendrites receive activation from other neurons. Soma, or the body, processes the incoming activation and converts them into output activation. Axons act as transmission lines to send activation to other neurons, and synapses, the junction that allows signal transmission between the axon and dendrites. And of course, the process of transmission is by diffusion of chemicals called as neurotransmitters. Okay, for example, acetylcholine or GABA or serotonin or dopamine. These are like several transmitters which are commonly occurred in human beings. Okay. So how the process, how the information is processed? A similar kind of thing will be translated into your neural network. Signals are received which are referred to as inputs from outside world or by the brain, and certain processing is done on these signals. It is biologically observed that the inputs are summed up by giving appropriate weights to the inputs, and each neuron receives inputs or signals from large number of other neurons. Okay, and you can see after combining these inputs, it sends output signals to a large number of other neurons, and lastly, final outputs or responses are given through sensory organs depending on the strength of the summed inputs. This is actually, you are going to see that how this is exactly mapped into the artificial system. So basically signals are received and these signals are summed up. If the signal is above a threshold, then some action will be taken. If the signal strength is lesser than some threshold, action will not be taken. And accordingly, if the action is to be taken, then that information will be passed on through the sensory organs. Okay, so that it is said like depending on the strength of the summed input. You can see like the brain integrates and stores the past experience, which could be previous classification of input data itself, or organizes experience. Like already I told you, like if you have been trained on certain aspects, definitely you can remember those things and you can use that knowledge to tell. Like if I show you this object, and ask you, so what this is, then you can immediately tell, sir, it is a water bottle. The reason is that somebody has already told you, you need to call such object as a water bottle. Where it is stored in the brain and in the form of electrical impulses. Whenever required, it is recalled. And you can see what, if I ask you, you get sense from your ears and it goes into your brain, and then it is processed, and finally it is the output is like you speak out that it is a water bottle. So such things are actually happening in your information. And of course, you can see like brain is having tremendous capacity to do this. Okay, you cannot just imagine. I already explained this supervised and all. Yeah. So let us now see what is an artificial neural network. This is just like imitating your actual human neural network, and you will see that it is a structure composed of a number of interconnected units. The functioning is same. Each unit has an input or output characteristic, and it implements a local computation or function, which is actually nothing but like collecting the all inputs from every neuron and then summing up, and the signal is formed. Depending on the signal strength, the output is determined whether to fire or not. Okay, so the output of any unit is determined by its input output characteristics. its interconnections to other units and external inputs. You can see like briefly, this is the research history of artificial neural network. I should just try to highlight this particular person, Rosenblatt. Rosenblatt was the first to define or develop what is called as a perceptron. Further, because of some issues with the perceptron, like it was really fantastic, but it could not handle the situation of nonlinear separable case, and therefore the results were like not accepted worldwide, and it was proved by Minsky and Papert in 1969, and because of which the research on ANN was actually stopped. Many people just ignored this artificial neural network in the period of 1969 to 1980, and only after that people re-looked at this and tried to develop some important milestones in this particular field. Now it is like one of the widely used techniques. Let us see the first model, which was proposed by McCulloch and Pitts in 1943, and it is the most like simplest neuron model. You can see that the variables x1, x2, x3, so on up to xk, they are actually nothing but inputs. Okay. When I say x1, x2, so on up to xk, they are inputs. They are actually nothing but the observations on the different characteristics. These observations are combined with some weights. Okay. And this is actually something like, okay, the strength of the signal. Okay. So all these are combined with some weights, and that weights along with these are summed up over here. This summation unit or summing node is actually nothing but like summation xi wi, or you can put it like wi xi. It just linearly combines the input with some weight, and the summing node is obtained. Once the summing is done, then the summing is actually, meaning the strength of the sum is decided using some function called as threshold, and accordingly the output is obtained. You will understand these things shortly. So you can see like McCulloch-Pitts neuron model has 4 components. The first one is input values, then vector, weight vector, output value, and threshold value t. Threshold value is actually nothing but a function. Okay. So, so I have still half an hour for this. Yes. So synaptic weights. The weights vector or weight vector is actually nothing but a synaptic weight vector, and it actually takes information from one neuron to the other neuron. You can see a set of synapses of each of which is characterized by a weight or strength of its own is called a synaptic weight. And you can see the values W1, W2, so on up to Wk are weights to determine the strength of input vector X. And you can see the net is obtained using this formula, that is summation xj wj. Net is actually nothing but the summing of entire input. And this threshold or threshold for neurons, that's what I was telling, that unless a particular threshold is reached, meaning unless a particular strength is reached, neurons will not fire. So that threshold value is determined using some function, say threshold function like this. A threshold function is either a binary type or a bipolar type. You can see this is a net on the x-axis. If net is 0, that means if net is up to this point, there is no firing. As soon as net goes beyond this, definitely there is a firing, and you can see that the neuron has fired, and you can see like for net greater than or equals to 0, yi, that is output is 1. For net less than 0, output is 0. So this is like how some threshold is obtained. A threshold is put at 0 over here. Like if you have positive net, you classify the observation as 1. If you have negative net, you classify the observation as 0. What are these ones and zeros? Ones and zeros are nothing but the classes. 1 is representing, say, class level which you are interested in. Say, for example, buying a computer, that example you can remember, in which yes is the thing which a store manager may be interested in. So he may label yes as 1, no as 0, and so on. So accordingly, if the net for that particular example happens to be greater than or equals to 0 for some appropriate weight vectors, which if exist, then you can have the label to be classified as 1. That means yes, the person will buy the computer, and otherwise no. Then how one trains this model? Now let us try to understand, like training. I am not using the word fitting because in statistics we usually say fitting of a model. Fitting of a model is done by estimating the unknown parameters involved in the model, wherein a model is already decided. But in this particular case, you can see that there is no fitting. The reason is that we don't have a model. We are trying to learn the pattern from the data itself, and that learning is done using certain architecture. Here we are trying to imitate the human learning system from the data. Okay, so we are trying to make the computer learn from the data itself, so that when a new observation is given, it will automatically predict the class with much accuracy. Okay, so in this process, like how the things are done. So for that, you just need to assume a training data of the form like n data pairs xi di. Di is your desired output. Xi is a vector which is having observations on, say, some features or characteristics of the objects. Okay, the objective of training the network is to obtain a set of weights wj's, which is similar to finding estimates of coefficients in a linear regression model, such that network output y is close to the desired output d. So whatever is obtained as a network output, we denote it as y, and the desired output, that means the label which is already available with us, we call it as d for all observations. And the closeness of this this desired output and network output is measured using error function. Error is defined as like half of di minus yi square. Usually it is summed over all possible i's. Okay, so what is the procedure? The procedure is like this. What we do is, in the first step, we select an initial set of weights, and these weights are actually randomly selected either from uniform 0, 1 or uniform -1, 1. And we start with like setting or initializing our error terms as 0. Then we choose any input vector xi and compute net. Okay, we are having such n inputs. Remember, we are having n different input vectors, and we are combining them to get what is called as net. Then we compute the neurons output yi using the rule yi is equals to 1 if w0 transpose xi is positive, and 0 if w0 transpose xi is less than 0. You can either put equality on the other side in the first one or in the second one, depending on your need. After applying each input xi to the neural network, weights are updated. This is an important step in the process of training neural network. One needs to update the weights, and weight updation formula over here is like this. At rth stage, the wr plus 1, that means r plus 1th updated vector of weights is updated from rth stage weight vector, say wr, plus c into di minus yi into xi, where c is a constant. C is a constant, you can call it as a correction term, and this is user defined. One needs to define it on your own. This is not learned from anywhere, and it can be decided based on you can do trial and error on this, or you can do some cross validation for identifying the best possible value of C, so that your complete data is classified correctly. Complete training data is classified correctly. Further, you can see in step 5, we compute error term, and we see that the error term is actually added. You can see error is added, meaning for every I, the error is added. So you have to complete this one cycle for all observations. Okay, so once it is done, then you check whether for all n observations, whatever the error is obtained, whether it is less than some threshold. This threshold is again actually defined by the user. You call it as some pre-specified small number. If the total error is less than delta, where delta is pre-specified small number, then you stop. But if it is not, then again you set your error to be 0. You start with the updated weights, go back to the step 1 and start a new training cycle. Continue this until your error is less than the threshold, or you can say the pre-specified number delta. You can see like this is the basic structure of artificial neural network. Earlier I didn't mention, like only I mentioned only as a threshold, but threshold is actually a function. It is an example of one function. You can see you can have in general what is called as activation function. Why the word activation function? Activation is like whether the neuron should be fired or not, whether the neuron should be activated or not. That is actually based on this function. So if the function is beyond certain threshold, you can definitely say that it is activated. You can get your desired whatever the output you want. So output will always be there, either in the form of fired or not fired. Okay. A similar kind of thing can be done in, if you change the activation function, if you just remove it and make and didn't put any threshold on that, you can just have any other function like sigmoid or double sigmoid and so on, which can be used over there. You can get continuous output as well. You can see like this is completely the processing unit of the neuron. Yeah, so these are like different types of activation functions which are used in this particular setup. One is threshold, then piecewise linear, sigmoid, double sigmoid, and so on. Already I have explained this. This is a piecewise linear. You can see up to here it is 0. From here onwards it is 0 only. In this span it is non-zero. You can see this is one of the popularly used function in the field of artificial neural networks called a sigmoid function. And this is S-shaped, and you can see this is exactly same as the logistic regression model, wherein this net is nothing but xi transpose beta. And this is actually not for y, but it is actually used for pi, where pi is probability that y equals 1. So probability of class 1 is actually modeled as a sigmoid function in logistic regression. Same activation function can be used in artificial neural networks as well. And one step ahead, one can also think of like double sigmoid function, which is defined using this formula. These are like different graphs of a sigmoid function for different values of lambda. You can see as lambda changes, the nature of this function changes. You can see it is a S shape, and the location is same, only the shape of the function changes. Of course, it retains the shape of being S, but only like the curvature and all, they change as you change the value of lambda. Lambda is again a user defined entity. What type of function you are putting, that is actually characterized by the value of lambda. Now, when we are actually having a function which is nonlinear, earlier we were talking about a linear thing, but you may have a nonlinear thing in practice. And if you have a nonlinear setup, how do you train the model? You can say artificial neural network using a nonlinear activation function. And here weight updation is not that easy. Here you need to work out the derivatives of certain terms so that weights can be updated. This is just like your Newton-Raphson. You can see like in Newton-Raphson, how do you update the weights? A similar way, weights are updated in this particular setup as well. So you can see like your yi is f of net I. Net I is actually nothing but summation at ith node, okay, or the net output at the ith node. And you can see goal of training ANN is to produce yi such that it replicates corresponding expected output di, and we want our yi, that is f of net I, to be approximately same as di. And the error is actually measured using this term, which we have already seen. Now, to find weights, or rather to update weights, what we need to do is we need to differentiate this error function with respect to weight vector. But you can see this function is actually function of f, and further it is function of net. Net is actually function of w. So you can use your basic calculus and apply chain rule of differentiation to work out the derivative of error function with respect to w, which is something like this. Finally, you can see that the derivative is given by this particular formula. So once you have this derivative, one can easily update the weights. You can see the weight updation formula in the next slide. Initially, choosing arbitrary weights W, the weight adjustments for iterative procedure is given by, you can see like here we should have like updated weight is equals to old weight minus eta. Eta is a constant usually called as a learning parameter or simply learning rate parameter or learning constant, and accordingly the weights will be updated. Whether they will be fast or small, it depends on like, meaning how weights will change, whether weights will change drastically or slowly, that will be actually decided by this eta. So eta is a learning constant. Usually people set it to be like 0.5 and they proceed with the learning procedure. But you can verify, or you can practice with some different learning rates also. You can play with your system and you will see like which network is better and which one is not. So dou E by dou W is actually from this particular equation. You can see which is obtained using chain rule of differentiation. So yeah, so you can see the same formula written over here in terms of R. So R plus 1th stage, this is the updation of W. So this is a slide which talks about different types of neural networks. Neural networks are of actually basically there are two types. One is like feed forward and other is recurrent or feedback. Because of their complexity, these models complexity and not even like producing much better output than these models are not studied further, and only people are studying feed forward networks. I shall explain what do we mean by feed forward. There is only one directional flow of information. There is no flow of information in the reverse direction, so that they are called as feed forward. Information flow is from left to right. As far as that structure which I shown, in the same structure, it is information is flowing only from left to right. It's not from right to left. You can see there are several versions of the single layer perceptron, multi-layer I am going to talk about right now, and radial basis function nets. And it has not yet stopped at this, but there are several other versions of neural nets like CNN and so on, which are currently used for pattern recognition. Okay. So yeah, single layer already we have seen, so I am not going to focus much on this. But why it is feed forward, I will say it is feed forward because the information is carried in this direction only, not in the other direction. And in case of regression, now what is happening? So if we are now trying to focus ourselves on the regression aspect, so this was all about like classification earlier. In case of regression, we are having k independent variables, which are actually nothing but like your input vectors, you can say, in classification. And you can see like these are your regression coefficients, which are replaced by your weight vectors in artificial neural network. Here we are having a regression function, which is an activation function in neural network, and this is your y, that is estimated response, or I should say predicted response. This is a general setup of regression, and I guess you have already studied this in the previous class, wherein the speaker was talking about like handling outliers in regression. So I am not giving much attention on this particular slide. These are the basic assumptions, but remember, these assumptions may not be satisfied in real life, and you need an alternative to the traditional method of fitting such a model, that is least squares method. So we cannot always rely on this, and we need to have something which will not depend on the model. We need something which is data driven. So how do we do that? Of course, in case of regression, the parametric approach is to estimate betas using method of least squares, and you can see the least squares estimator is given by this particular formula. But if you see the differences, you can see ANN. In ANN, the term inputs is used for x1, x2, xk. In case of regression, we call them as regressor variables or predictors. The regression coefficients in regression are called as weights in ANN, and estimation of weights is called as learning. Here we just say estimation. Here ANN model output is actually the estimated value of response in regression, and there is a bias term which we call this W0 is called as bias, this beta 0 is called as intercept. Terminology is just different. Otherwise, if you keep the relationship linear, both are same. We can see like the comparative study of this. You can see like if you generate regressors from uniform distribution and error from normal distribution, and if you generate response according to this with different sample sizes, and if you repeat the same simulation design for 100 times and compute the averages of the estimates obtained using ordinary least squares, which I showed you earlier, artificial neural network with identity link function, ANN with sigmoid activation function, the results you can see over here. You can see the residual sum of squares. Okay, ANN with sigmoid performs better than OLS. You can see it performs better. Of course, since the model is linear, there is not much difference between the residual sum of squares of OLS and ANN. But if you have a multi-layer network wherein the nonlinear setup can be handled properly, since it was linear, all the observations were satisfying the assumptions of linear regression, OLS is the best one. It cannot be beaten, and thereby even neural network training was not much better than OLS. But when the assumptions are not satisfied, you can definitely expect better performance by ANN over the least squares method. As I told you, like Minsky and Peppert claim that the existing perceptron model given by Rosenblatt was not of much use because of like the weights may not always exist, and therefore they actually proposed like a series of perceptrons which can be put together in the form of like hidden layers, and a more complicated structure can be formed and learned from the data, but that will be like more advanced. The idea was just generated, but it was speculated by them that training such a model would be more difficult, and because of that speculation, which many researchers took it for granted that it is difficult to do that, nobody did for almost 10-11 years, maybe like 1969 till 1980s. Nobody from 1969 to 1980s, nobody bothered to develop a training algorithm for a multi-layer network. That was the black period for artificial neural networks. So you can see one extra layer has been put. So you can see this is input layer. Inputs are combined with weights, and output is computed. Again, output are in different form, in different ways. Those outputs are again combined with weights in the later stage to produce final output. Number of hidden layers could be more. One can have one hidden layer, two hidden layer, three hidden layer, and so on. But it was later on theoretically proved that only one hidden layer is good enough to approximate any nonlinear function. So people usually go with only single hidden layer model. But again, the question remains unanswered: how many outputs or how many neurons should be there in the hidden layer? And there are several research papers you can see which address this question, like how many neurons should be kept in the hidden layer. How this feed forward network is trained. Feed forward network is trained exactly in the same manner using an algorithm called as back propagation algorithm, which was discovered only after 1980s. Okay, it was not available before, and this was like rise of neural networks once again, that such type of networks can be trained to do some fantastic jobs. And what was that? Again, the use of like chain derivative, chain rule for derivative, and weights were updated accordingly. You can see some fancy mathematics over here. I just don't want to get you into the details of that, but I shall tell you that weights can be updated. I shall show you the formula for weight updation in both the stages. So from weights are updated from hidden unit. Okay, let me show you the earlier one. Where it is, yeah, HPJ So yeah, back propagation. First this and then this, right? So as the name suggests, back propagation. First, you can see why the name back propagation. I shall tell. First, these weights are updated, and then these weights are updated. So information flow is in this way, but only way is like the network is updated in the reverse direction. Okay, meaning first these weights are updated, then these weights are updated, but the model is feed forward. Information flow is from this way, but network updation is in this way. So that the word back, so that the name back propagation. You can see, yeah, this is the formula for updating the weights, wherein dou by WRJ is actually worked out using, yeah, it is here. It is here, over here. Over here you can see the derivative. Okay, and similarly, the weights which are present from, like weights from input unit to hidden unit, they are updated at nth stage like this. Again, using the same usual differential trick. Then how the algorithm works? Algorithm works in the same fashion. Only thing is that, like, you start with like initial weights W and V, learning parameter is eta, and we set our errors to like 0, and then we choose input pattern, we compute output of layer, compute error value, output layer weights are adjusted, then hidden layer weights are adjusted, so that the name back propagation. And then if p is less than p, then we go to step 2. That is meaning is that if the output, if the error is less than the threshold, then we actually, this is p is like we are training every observation. If the if only less than n observations are trained, we are again going to go back until all n observations are trained. Once n observations are trained, then we check the total error. If total error is less than the pre-specified number, say E max, then we stop. If it is not, then we again set our error to 0 and repeat the procedure from step. Okay. So this is an example which is actually about the artificial neural network with regression. I shall show you that for model 1, which is a non-linear thing, model 2 is also non-linear, 3 is also non-linear, only 4 is linear. You can see the prediction error for different methods. OLS, this is the prediction error. Non-linear least squares, this is the prediction error. Multi-layer feed-forward network with backpropagation learning, this is the error. You can see more or less. Okay, this is like this non-linear OLS is like, you know, the relationship. You can just remove this, then definitely these are the things which are MFN doesn't assume any relationship. Non-linear least squares assume some relationship, and that assumption may not be valid always. And of course, this assumes linearity, and which is not good. You can see at only for model 4, because model 4 is linear, so that OLS cannot be beaten by any other method. These are the references. So that's all from me in the first session. If you have any doubts, you can ask. Yes. Any doubts? Anything which on which you need clarification, you can ask. I'm just checking the chat box if there are any questions. Yeah, no questions till now.
Participants, feel free to discuss with sir.
Yeah. I hope I was not too fast.
Sir, take break, sir, then come back. How many
Okay then.
minutes sir, take break, sir?
15 minutes. I'll just make coffee and I'll have some coffee and then I'll come.
Okay. 3:45. Okay, sir. You come
Ah,
back, huh?
3:45. Okay, you'll start at 3:45.
Okay. Participants
Uh,
return from 3:45.
okay. I'll not leave the call. I'll be in the call itself. I guess that is fine. Or shall I leave and then again join? What should I do?
No problem, sir. Both
Okay.
of you is there. No problem, sir.
Okay. I'll
Okay.
leave and then join. Okay.
Okay. Okay, sir.
Okay then.
Okay.
Bye.
Sir, Deepak sir? Deepak sir? ஏம்மா ஆஃபீஸில் பிடிச்சிட்டு வாங்க, கொடுக்க சொன்னா அவங்க பிடிச்சி தந்துருவாங்களாம்மா? அப்படியாம்மா? தீபக் சார்? ம் 48 ஆயிடுச்சுங்க. இல்லை இல்லை, சாருக்கு என்னென்னா ஒரு வேளை ரீசார்ஜ் ஜாயினிங் இஷ்யூ எதுக்குன்னு எனக்கு டவுட் ஆயிடுச்சு. வர்றது லேட்டாக வர்றது பிரச்சனை இல்லைங்க. ஜாயினிங் இஷ்யூஸ் வாட் ஆஃப் ஐ டோன்ட் நோ அண்டர்ஸ்டாண்ட்.
Yeah, Dr. Gandhiya, shall we start?
Yes, sir.
Okay. So, welcome back to the second session of this day, and I am again back to discuss about another technique which is popularly used nowadays in the field of machine learning, and it is called support vector machine. So, the support vector machine is actually uh, uh, I should say a combination of two different methods. One is support vector classification and other is support vector regression. So we shall see both like classification and regression using support vector machines. Before talking about support vector machines, let us uh, uh, realize like how a new observation is classified into either of the classes using uh, neural networks or even using any logistic regression classifier or so on, which has kind of a linear combination. Okay, so in that aspect, we can see that we actually want the uh, the the point to be classified into either of the classes with more confidence, and that confidence can be achieved if we have a good separation amongst the data points from two different classes. So let us try to understand like if we can have a margin in between the two data classes, meaning the classes which are appearing naturally in the data, then in the margin, of course, there will be no data point, but we can have like good separation. Just imagine a highway. I guess most of you might have seen NH48, which connects Pune with Bangalore, and further, I guess it runs, yeah, Pune with Bangalore only. It's not running up to Salem. In between, it is checked. Fine. So from Pune to Bangalore, you can see there is a good partition. It is almost a 6-lane highway, and there is a partition which is called as median. Okay, median of the road. That partition is actually taking almost a space of 1 lane. You can see actually there are 7 lanes on this side, 3 on the other side, 3, and in between the partition there is one more lane which is actually used for partition only. No vehicle runs on that particular lane. It is like done for beautification. You can see like several things are already planted, like plants are there, and it is like a multi-purpose. It is separating the 2 lanes. Secondly, it is also hiding the light from the opposite vehicle. The idea of putting this particular partition is to like separate the 2 lanes as far as possible, so that there will be no collision of the vehicles coming from the opposite direction. A similar kind of stuff is actually, so just imagine another road wherein just only a line is drawn. Okay, so now people are actually tempted to get into the opposite lane and overtake and again come back. During this process, there is a high chance that some collision may occur. So if we have a good like a thick margin between these 2 lanes, then definitely a substantial reduction in number of accidents can be achieved, as against like very thin margin. The classifiers which we have seen, like classifier like logistic regression I spoke out, and even those decision tree and other classifiers, they are having actually like particularly on neural network also, it is having a very thin margin. Okay, and it is just like below that point, above that point. If you remember, there was a threshold function, and using that threshold, you can see like below threshold, if the net falls, then you say that class is 0. If above threshold the net falls, class is 1. So that threshold itself is a line drawn, you can say, and it is a very thin line which is used as a classifier. It can be a hyperplane in higher dimensions, it can be a line in 2 dimensions, and so on. It can be a plane in 3 dimensions and so on. So can we come up with not just a thin line, but a kind of a margin which can separate the two classes in a proper way? This is the idea, and it is possible, and one can construct what is called as a large margin classifier. Let us see what are these large margin classifiers. So already we have seen these things. So yeah, I shall come back to this comparison slide later. Okay, fine. So let me use the board and then I shall come back to the presentation. Can you see the board now?
Yes, Professor. Yes, sir.
Okay. Okay.
Is
So
streaming.
let us try to understand the concept of margin. Okay. So let us imagine that we are having such kind of data. Just imagine these are straight lines parallel to each other. My drawing may not be that good. Okay. Now I am having some data points on this side and some data points on this side. Okay. Just imagine for the time being that this line is like a dotted line. Okay. I shall just make it a dotted kind of stuff. Okay. A dotted line. I don't want it to be continuous. This is like an invisible line. Okay, fine. Now this is the thin line which we were actually finding. This is, say, for example, class C1. This is, say, example for class C2. Class C1, say, is denoted by 1. C2 is denoted by 0, for example. Or we shall be changing our notation shortly, and we shall see like how this can be found. So if we are actually trying to classify, then if the point is somewhere here, say for example, I have another point, let me call this as point A, here is, say, some point B, and this is point C. Now, okay, let me just put this point C very close to this. Okay, so C is somewhere here. Now, if we are actually trying to classify this point A, we can do it using this classifier. You can see this is the separating line which separates class C1 and C2, and this point is much away from this separating line. So according to this classification rule, or whatever the discriminating line we have, the class label assigned to this point A will be C1, and the confidence associated with this label will be very high. The reason is that the point is much away from this discriminating line. At the same time, if we talk about this point C is very close to this particular line. And if at all we apply this rule, definitely this will classify it as C1. But if there is a slight change in the rule, this point may be classified as C2 also. It may fall below this particular line as well if there is a slight change in this line. So basically what we want is, like, if we want our classification to be confident enough, instead of developing a single line or a hyperplane, this is like just a two-dimensional projection of a three-dimensional data, you can just imagine, like, if we can develop a kind of hyperplanes which are separating one class, or meaning they are holding one class on their one side and the other class on the other side. If we can do that, then we can be able to find a particular separating hyperplane which will be classifying the observations with much confidence, unlike our usual classification techniques which were like artificial neural network or even logistic regression and so on. So how does one measure the distance of a point from the hyperplane? So if we have a point over here, we can measure the distance of that point from the hyperplane using the formula like this. So if usually a hyperplane will be denoted by W transpose X, or simply W dot X. X is a point over here, plus B is the intercept term, it is a scalar. You can call it as a bias, and this equals to 0. This is actually nothing but the equation of this hyperplane. Okay. So if one wants to develop write the distance of the hyperplane, distance of the point from the hyperplane, then the distance, okay, if the point is on this side, then the distance can be found using the formula absolute of, you can put it in this way, W transpose X plus B divided by norm of W. This is nothing but distance of, okay, distance of the point with respect to the hyperplane characterized by the weight vector W, and B is a scalar. Let me just alter this. B is a scalar, and of course evaluated from the point X. So this is like distance of the point X from the hyperplane characterized by the parameters W and B. Now, what we are actually interested in, like, you just forget about this point C for the time being, and let us have like one more point. Okay, yeah, one point over here. We can see that we want the distance of this point, the smallest distance of this point, to be as large as possible. That means we want a hyperplane which should be kept as large as possible from the data points falling in class C1. At the same time, we are again pushing, if we apply the same rule on this class, again we want the smallest distance from the data points in class C2 to the hyperplane to be as large as possible. So we are trying to maximize the distance, which is the shortest distance of the data points in a class C1 or in class C2. Now with a slight change of notation, I shall just denote, yeah, this I shall keep it as 1, I shall keep this as -1, just for the sake of mathematical nicety. So this particular hyperplane, its equation will be W transpose X plus B is equals to 0. This equation will be W transpose X plus B equals to 1, and this will be having like W transpose X plus B equals to -1. So anything like, if you have so if I say W transpose X plus B, W is actually a weight vector, W transpose X plus B greater than or equals to 1, if I say, it means the points which are falling above this particular hyperplane. If I write it as less than 1, it will be below. Below we are not bothering about for this hyperplane, but we are bothering about below for this hyperplane. So we shall write W transpose X plus B less than or equals to -1. So accordingly, we can see that above region or below region of an hyperplane can be defined. Now, what we want is that the distance of, minimum distance of every data point in this class should be as large as possible from this hyperplane. At the same time, minimum distance of a point from this class should also be as large as possible from this hyperplane. So the distance of these points can be written, okay, as like distance of the points from the, I am writing now distance of the point. So let me put it formally. So actually what we want to minimize is some distance. So if I have 2 points, xi is a point in class C1, xj is a point in class C2, then what I want is the distance between the hyperplane characterized by rho and w with vectors xi and xj to be something like minimum distance. Okay, minimum distance taken over whom? Taken over xi, such that value of yi is +1. With whom? With the distance like d of w b xi. And this should be added. We are having both the distances. This should be added to minimum of distance of xi from the hyperplane with yi is equals to -1. Yi is equals to -1 indicates class C2. This is now xj, because we are having xj coming from C2, distance of the point xj from the hyperplane characterized by w and b. Okay, which is actually nothing but using the formula for computing the distance of a point from the hyperplane, we can see this is nothing but minimum over xi. Okay, yi is equals to 1. This is absolute of w transpose xi plus b divided by norm of w, and plus again minimum over xj yj equals to minus 1 absolute of w transpose xj plus b divided by norm of w. And which you can see further, when you have yi is equals to 1, this w transpose xi plus b, which is a point on this hyperplane, when yi is equals to 1, you can see this point is almost, you can see the minimum distance will be, this hyperplane will be drawn very close to this particular point, which is the minimum, which is at the very shortest distance from this point. That hyperplane will be somewhere around here. It will be satisfying equation of this, that point will be satisfying the equation of this hyperplane, which is given by w transpose x plus b is equals to 1. So if xi is on this hyperplane, this should satisfy the equation, so that w transpose x plus b will be having value 1. Similarly, if xj is on this hyperplane, then it will satisfy the equation and the value will be minus 1. So accordingly, you can see this minimum, of course, 1 over norm w doesn't have any yi or xi over here. It will be just taken out norm of w into bracket. This is absolute of 1. I shall put plus absolute of minus 1. Put together, this is simply 2 divided by norm of w. And you can see this is the thing. This is called as actually the margin. This is called as margin. So a margin needs to be maximized as a function of weights, so that the classification can be achieved with a greater accuracy. But remember, this classification will be done with the help of some function. So what will be that function? So the function will be actually written in the form yi into w transpose xi plus b. B is a constant greater than or equals to 1. You can see earlier this linear combination only was greater than or equals to 1. Greater than or equals to 0, you classified it as 1. And if it is less than 0, you classify it as minus 1. Here we are multiplying this by yi, where yi takes only two values, 1 or minus 1. Accordingly, the rule is designed. So the large margin classifier is actually obtained by maximizing the margin. Margin is 2 divided by norm of w, okay, subject to the constraint over here, subject to this constraint, so that whatever the weight vectors we get, the weight vectors are finally used to predict the class of the new observation through this particular equation. So this is actually the concept of large margin classifier. Now we shall see an example of a large margin classifier called as support vector. The support vector machine is actually, it was introduced by Vapnik, Vladimir Vapnik, and he actually got inspiration from the work of Rosenblatt and Minsky and Papert about artificial neural networks. And Vapnik and his co-workers, they actually worked on the development of this this method to come up with a novel technique for classification as well as regression, and it was presented in a conference abbreviated as COLT, C-O-L-T, in 1992. And you can see, like, the word support vector was explicitly used for the first time by Cortis and Vapnik in 1995. They introduced their method in 1992, but the term was explicitly used only in 1995. Actually, it was a very famous method for identifying the objects in images. So the input to this method was like an image. Of course, you need not have only images, you can have input in many forms. Only thing is that you have to convert your input in the form of numbers. Even an image can be converted into numbers, and accordingly classification can be done. Okay, and you can see like it gave accuracy comparable to neural network with hand designed features in a handwriting recognition task. That was a very path breaking achievement over there. You can see like handwriting recognition can be achieved using support vector machine. Even identifying fraud signatures can be done using support vector machines. And nowadays you may be having some software which recognize the handwritten material, and it convert it directly into typewritten form. That is again based on support vector machine. Even speech recognition devices are available. You might be watching some ads also of some cars which actually take instructions in the form of voice. Okay, or you can say voice commands. And even in your mobile also you may have a voice search or voice command search and so on. All these things are actually nothing but like artificial intelligence part. In the background you will see machine learning techniques. You can see like currently SVM is widely used in object detection and recognition, content based image retrieval, text recognition, biometrics, speech recognition, and so on. Even for like when you Google out something, you will see that only specific content concerned with your keyword which you have Googled out, that content will be only appearing on the screen. Of course, then it is manipulated with certain algorithms so that those which are paying for their pages to appear in the first three positions, they will have, or if there is no such thing associated with that, then the content will be organized according to the classification rule. Okay, so there is like information retrieval, and the retrieval can also be based on like images as an input. Okay, let us see what are these support vector machines. They are actually nothing but they are tools used for optimally predicting the class membership or real value of unseen outputs that are generated or characterized by one or more inputs by means of looking at some available training input output pairs and then building a model based on the observed input output relations. In short, something is given as an input, that something is actually nothing but the measurements on certain characteristics of an object, and the output could be either a class membership or a real value. And all these things is actually done based on a trained data. So training is actually first done, and once the training is done, then based on that trained model, this goal of classifying or attaching a label to a new observation is achieved. This can be done using two different approaches. One is support vector classification and the other is support vector regression. I shall try to throw light on these two aspects of support vector machines. Let us first get introduced to some notations, and you will be seeing a lot of mathematical aspects in this particular thing, but I shall try to keep it as simple as possible, because without understanding the background of in terms of mathematics, just studying support vector machine is of no use. I know that you can apply these methods using any software without knowledge of what is happening in the black box, but you will be on advantageous side if you know what is happening in the black box. Accordingly, you can make the interpretations and you can adjust the things in a proper way. So let us see the mathematical background of support vector classification, and then we shall get introduced to, if time permits, support vector regression. Okay, so the input vector you can see is denoted by x, y is output, k is dimension of input space, n is training set, n is actually size of training set, or you can simply say number of observations, w is your weight vector, those two lines, they actually denote norm of vector W. Norm is actually nothing but the Euclidean distance of vector W from the origin. It is simply under root summation Wi square, ironing from 1 to k. B is used for bias, and alphas are actually nothing but Lagrange's multipliers. Definitely you might be wondering, if Lagrange's multipliers are there, then there may be an optimization problem to be solved, and I'm sure we are definitely going to look at the formulation of the problem. Okay, and you can see like xi are slack variables, and xi dot xj denotes the dot product of vectors xi and xj. So let us see, like okay, there are like two cases. One is linearly separable case and the other is linearly non-separable case. So we shall try to throw light on both linearly separable as well as linearly non-separable case. In linearly separable case, you can always find a hyperplane which can separate the two classes perfectly. Okay, so that the case is called as linearly separable. And hyperplane, I am talking about this word hyperplane. Many of you may be knowing, many of you may not be knowing. And hyperplane is actually a plane in higher dimension. Okay, you can imagine its lower dimension variants as in 2 dimensions you have a straight line. The straight line becomes a plane in 3 dimensions. And if you go beyond 3 dimensions, you call it as an hyperplane with the same equation. It is linear in nature, and so that if you can always find a hyperplane which can separate the two data, meaning separate the two classes clearly, you say that the situation is linearly separable or the data is linearly separable, and you can go with the assumption of like linearly separable data and proceed to find out a support vector classifier. So yeah, so you can see like the goal is to establish the equation of an hyperplane that divides D. D is your data set, leaving all the samples of same class on the same side while maximizing the minimum distance between either of two classes and the hyperplane. This minimum distance between either of two classes and the hyperplane is nothing but margin, which I just derived it for you. It is nothing but 2 upon norm of W. Okay, so you should not be surprised to see that in the objective function you will have like 2 upon norm of W for maximizing, or if you just convert it into the minimization problem, its reciprocal can be used, like 1 by 2 norm of W, minimize 1 by 2 norm of W. Both the problems are equivalent. So this was the linearly separable case I was talking about. The two data sets can be separated using hyperplane, and you can see one observations belonging to the same class are on the same side of the hyperplane. This is the hyperplane. You can see they are falling on the same side, and you can see these observations are also falling on the same side. But this hyperplane is very close to these observations, whereas it is far away from this. So it's not definitely desirable. Then which hyperplane is desirable? You can draw infinitely many hyperplanes in between these two lines, which can separate the two classes linearly. But the problem is whether which one of them is optimal. So we need to find the optimal one. So the optimal one which will be the one which will have the farthest distance from both the classes, from this class observations as well as this class observations, so that the distance between these two lines, these two parallel lines, we call it as margin, so that the margin will be as large as possible. This is the one which is desired, the one which will lie exactly in between these two lines. This line is called as a supporting hyperplane. This is also a supporting hyperplane, and this is called as separating hyperplane. The name supporting is because you can see it is just touching the points in the class C2. Similarly over here, some of the points may be on the hyperplane or may be very close to the hyperplane. They need not be always on the hyperplane, but they may be very close to the hyperplane. Accordingly, we have to find the these two hyperplanes, and then the third one. Of course, our target is to find the middle one, because that is the only thing which will be used for the purpose of classification. Okay, and not these two, but this will be obtained because of these two hyperplanes only, as you will see further that these points which are lying on this hyperplane and as well as on this hyperplane or close to these hyperplanes will have special meaning or importance in the computational aspect. So let us see like what is the model. Say for example, if we are having a linearly separable case, you can see a linear function can be used to define a classifier. So you can see like g of x is nothing but equation of an hyperplane. I have already explained this on the board which you while discussing margin. This is actually indicating the equation of hyperplane where b is where w has to be found. I can either you can put w transpose x or x transpose w, both are fine. B indicates the position of the hyperplane, and of course w indicates the orientation of the hyperplane in the p-dimensional or whatever the dimension we have that space. Okay, rather you can say in d dimension space, that means data dimension space, whatever you have. Maybe like if we have p components in x, it will be a p-dimensional space. So the orientation of hyperplane is actually guided by w, because it is nothing but the weight vector perpendicular to the hyperplane, and this perpendicular is actually drawn from the data point. The perpendicular is dropped from the data point on the hyperplane. In that direction we are having this vector w. So that indicates the orientation of the hyperplane. B indicates the position. So both B as well as W are important for the knowledge of hyperplane. B indicates position, W indicates orientation. Okay, fine. So already we have seen like positive side for greater than 0, negative side for less than 0 on the hyperplane equals to 0. And this was like a very primitive classification rule which we used. Like if this is greater than 0, we assign it to C1, less than 0, assign it to C2. And of course, yeah, so this can be done by any discrimination function. Now you can see like if you have like for every feature vector xi which gives yi as an output, you can see for xi in C1 you have yi is equals to +1, xi in C2 yi is -1. So that you can put like either this greater than 0 or you can just put it is greater than 1, that is more appropriate. Okay, so suppose P is unknown feature vector, we have to classify using W and B, then classification can be done using this approach. Or you multiply this by Y and check whether this is greater than 1, you can have whether it is belonging to class 1 or not. Okay. Now already we have seen like we want to maximize the distance between the closest point and the hyperplane. Which hyperplane? This hyperplane. So that you can see that we want is like W transpose x plus B to be greater than or equals to +1. This implies x belongs to C1. And if this is less than -1, we say x belongs to C2. Now combined together, we'll see that this is the thing which we are desiring, that is yi into wi xi plus b greater than +1. So this becomes actually a constraint in the optimization problem. You can see over here the equations I have mentioned. I know they may not be visible properly, but I'll tell this is like W transpose x plus b equals to -1. This is W transpose x plus b is equals to +1. And this is W transpose x plus b is equals to 0. This is class C2, class C1. And this blue line which you can see is actually the margin which we just derived it to be 2 upon norm W. Again, this is nothing but the two-dimensional projection of a p-dimensional data. So our target is to maximize this margin subject to the constraint that yi into wi xi plus b is greater than 0. Okay. So that's what is actually mentioned here. The definition of optimal separating hyperplane is given. You can see, so given a linearly separable set D, the optimal separating hyperplane which is in short called as OSH, is the separating hyperplane which maximizes the distance of the closest point of D. That I already told you. What are support vectors? The points nearest to the separating hyperplane. This is really important. That's why I told you that the points which are on the hyperplane, separating hyperplane, or on the separating hyperplane, they are called as, sorry, I should say not separating, supporting. Here, of course, you can say nearest to the separating because nothing is there in between supporting hyperplane and separating hyperplane. So you can have this definition like the points nearest to the separating hyperplane are called as support vectors. Actually, they are either on the supporting hyperplane or very close to the supporting hyperplane. Remember, I am using two words, separating and supporting. I'll again come back to this slide. This is a separating hyperplane. This is a supporting hyperplane. This is a supporting hyperplane. These points are, I shall just annotate so that you will understand. These points are support vectors because they are closest to the separating hyperplane. But at the same time, you can see they are on the supporting hyperplane or very close to supporting hyperplane. Such points are called as support vectors. They are called as support vectors. Further, you will see that in the optimization problem, if you know support vectors from a data, you don't need to know the other points. Only support vectors will be used to find this particular hyperplane. So that this it makes your support vector machine very much robust in true sense. Yeah, so margin is already defined. I have already explained about this. So margin is like 2 upon norm W. So yeah, so maximizing 2 upon norm W is equivalent to minimize W. Of course, you should write norm of W. Okay, because W is a vector. We cannot just minimize W as a vector. We can minimize the norm of the W. So thus minimize, so your objective function becomes something like this: minimizing norm of W. Norm of W is what? Norm of W is square root summation Wi square, which is can be written as W transpose W. So minimizing square root of W transpose W is equivalent to minimize simply W transpose W, and of course divided by 2. So either of this can be used. So this is your objective function and your constraint is like this. Remember, this is not a convex constraint. You need to use greater than or equals to. Okay, the yi into wi xi plus b greater than or equals to 1. So your problem is now convex. This is a quadratic objective function. Remember, this is a quadratic objective function and it is convex in nature, and this is a linear constraint which can be solved. So this problem can be solved using any standard quadratic programming solver. You can use either R software or MATLAB or any software which can solve a quadratic optimization problem, or you don't need to bother about it. Nowadays there are inbuilt programs which will do everything. You just need to give your data in form of X and Y in form of labels as an input. So you can even use the function SVM available in package, function SVM available in package E1071, I guess 1071 or 1068. This is an R package which has function SVM. You can directly give that command, and yeah, I'll show the program. You'll understand later. I'll show you the program and inputs also. So it will automatically do it for you. So you don't need to worry about like how to solve this. But let me tell you, mathematically, this can be solved using method of Lagrange's undetermined multipliers. And you can see that this method of Lagrange's undetermined multipliers can be applied. But again, the issue comes like the problem as such, even though it is convex in nature, solving it may be time consuming. A more simpler version of this problem can be achieved by converting this primal problem into its dual form and rewriting it in the form of its dual and then solving it, and then again getting back the solution in the form of primal. That is more appealing, and it is more fast, and a more efficient optimization algorithm can be achieved in the dual form. So whatever the present day solvers are available for SVM, they are actually based on dual form of this problem, and they are not using the primal one, because solution to the primal is more complicated. Let me tell you, there are inbuilt functions not only in R, but if you are having MATLAB, you can visit LIB-SVM. It is a library maintained by researchers for functions which compute or which fit, I should say, or which learn SVM from the given data. It is for MATLAB. Okay, so that can be done. Apart from these two, if you are having SAS Enterprise Miner, you can do all these things in SAS. You can do this SVM in Statistica. You can do SVM if you have a machine learning tool in SPSS. SPSS also comes with machine learning tool. If you have purchased that, definitely you can do SVM in SPSS also. And I'm telling you, like freeware is only R, and in R I shall show you the program later. MATLAB also comes at a price, so it's not free. Only in R you can do it freely. Of course, there is another popular software called as Weka, but I'm doubtful whether it comes with some virus or not. Weka is another popular freeware. Okay, but R is like totally safe and free. One can go with that, but it is not user friendly. You need to program. Those who are not from mathematics or statistics background, it will be difficult for them to do. Even those who are like those who are coming from computer science, I guess there will be no problem. Engineering people can also do this, but those who are from different disciplines other than this, it will be difficult for them to handle R. It is a programming software. There is no click in this. There is no like Windows, you can say, interactive dialog boxes which can be, in which input can be provided. There is no such provision. Now it was all about like fitting I shall show you the example also later. This was all about like linearly separable case. Now let us see like what happens when we have a linearly non-separable case. In this aspect, we shall focus our attention on these two data points, particularly this one and this black one. You can see this orange data point, which is originally belonging to class C1, is falling beyond this separating hyperplane. So as far as this separating hyperplane is concerned, this point will be classified as C2, that is 0. Okay, O meaning hollow circle I'm using to denote points in C2. So this will be actually classified as C2, whereas this will be classified as C1, and therefore there is a misclassification happening over here. And if this is happening, what could be the reason? The reason is one cannot draw only a hyperplane which will separate all the data points from one class with the other class. And therefore, you can see that there is no hyperplane existing in the current setup. So if you want to separate them, you can do that. For that purpose, you need to draw something like this, something like this. Okay, yeah. Now you can separate them, right? Isn't it? You can separate them if you have a separator of this form. A straight line is definitely not going to separate, and therefore the data, you say that it is linearly non-separable. Data is linearly non-separable. So how to tackle this situation? So this situation can be tackled in two ways. You assign some error with the classifier. And the error assigned is actually in the form of the magnitude or the distance of the point from this supporting hyperplane. It is denoted by xi I, and here you can say xi j, which is in this direction. Okay, this is belonging to this class, so you measure the distance. So this is kind of an error committed by your separating hyperplane in classifying these observations. So you accommodate this error in your objective function itself and write the problem like this. So your objective function is changed to half W transpose W is now modified to half W transpose W plus C into this. This is misclassification thing. This is cost attached to the misclassification. So cost, we are incurring some cost and we are trying to find W so that the cost is also minimized. Now, whatever we were doing earlier, like we were trying to find the classifier with maximum margin, now the scenario has been changed completely and there is something like misclassification occurring over there, and we need to consider the cost associated with the misclassification, and that cost is coming into the objective function. It's not just coming into the objective function. You can see the misclassification part is also appearing in the constraint, and it is something like 1 minus xi. Margins are now broken down. Earlier they were like rigid. We had a rigid margin classifier. Now it has become a soft margin classifier. Soft in the sense, earlier we were having like walls. You can see on this graph, this is kind of a wall. Nobody can go this side. This is again a wall. Nobody can come on this side. But it is not possible. You can see if you draw these hyperplanes, one point managed to come on this side. This point also managed to go on that side, and vice versa. It may not be just one. You may have more than one or two, and it may be not like equal number of points from this class coming on this side or from this class going on that side. It may not be that case. This is just for the sake of illustration. They need not be just one or two. They could be many. But if it is like too many, then you forget about doing this and you need to go for something else. So you can see that this is something like a soft margin classifier over here. Now, this can be again trained using, or I should say this can again be solved using your method of Lagrange's undetermined multipliers, and of course according to the domain knowledge, C can be fixed. There is some literature which says that usually C should be kept as 5, but there is no such guarantee that with C is equals to 5 your output will be good. So, but you can believe for some extent that it could turn out to be a good classifier. You can always check the metrics which are used to verify whether the classifier is good or bad for a particular value of C, and accordingly C can be chosen from the user's perspective. So this is something like okay, thought of measure of the amount of misclassification, and you can see this actually leads to a more robust solution in the statistical sense. This is because we are actually allowing some points to pass on this side. We are providing scope for the points to be misclassified, which could be statistically sensible. Everything may not be like predictable. One cannot predict everything with 100% accuracy. We can allow some scope for error, and that error scope is allowed in this particular setup. Okay, there is one more thing which is usually done. I shall talk about that in the regression presentation. That is usually done, like how one can do this. Like one can draw this type of curve in a higher dimension, meaning in the lower dimension, which could be looking like a straight line or an hyperplane. I should say hyperplane in a higher dimension. That is actually nothing but kernel trick. So that we shall see in the regression aspect. Yeah. So this is what I have already told. Slack variables are introduced. Yeah, so let us see one example. This is a data which is linearly separable, and you can see the R code. Yeah, E1071. If you can see the screen, this is the library, I should say, an R package which is used to implement SVM. Let me tell you, it has also function for ANN. You can do both ANN and SVM. So here I have shown only SVM. You can go for ANN as well. You can see the function used over here is SVM. The data it wants is in the form of a data frame. So this is a basic command, like x1 is your input vector, x2 is another input. So actually input is this. These are the inputs. You can see 1, 3, 3, 3, 1, 1, something like that. So they are like your inputs. And this is actually nothing but your class labels, -1, 1, and so on. This class label is converted into a factor variable, and a data frame is constructed, and a command SVM is called from this package E1071, and a classification is done. Cost is set to be 5 in general. Of course, this leads to your, once you put linear kernel, I shall talk about this kernel trick shortly so that you'll understand. It does usual, it assumes that data is linearly separable and proceeds with the solution. So you will see the output. This is the output. You can see kernel used linear, cost is 5, gamma is another parameter. This is actually coming from the constraint. This is your, I should say, Lagrange's undetermined multiplier. You don't need to bother about that. Number of support vectors is like 4. This actually is found from the data. Okay, there are 2 and 2. 2 support vectors from one class, 2 support vectors from the other class. This idea will be clear from the next graph. You can see all the points are separated. You can see this is a confusion matrix. -1, 1. These are predicted classes. These are actual classes. Actual class was -1. Predicted class is -1. 4 of the observations are predicted in that way. Similarly, 3 observations were coming from 1 and they are predicted as 1. So there is correct classification. And no observation whose actual class was -1 is predicted as 1, or no observation whose actual class was 1 was predicted as -1. Okay, so and so on. So this is the graph of the classification. You can see this is what we are talking about. This line or this hyperplane is your optimal separating hyperplane. Okay, this is output from R. Okay, you can have different colors. You can modify this. You can. This is like the default colors I have taken. This is your class 1. This is your class -1. You can see this observation, this one, and this one. They are support vectors. Okay, so there is actually an invisible supporting hyperplane over here and over here also at the same distance. Okay, it is not shown in this graph, but there is an invisible hyperplane. Okay, so you can see over there, and remaining observations are scattered around. Clear? Let us see a case of linearly non-separable data. This is another data which is like having again 2 variables, okay, x1, x2, and y is your class label. Again the same thing. Now what we are doing is like we have changed the gamma value. Gamma value is now, earlier it was like 0.5, now we have made it as 1. This gamma is actually the trade-off, you can see, and this is appearing in your linear kernel. I have just made a gamma to be 1 so that this linear kernel becomes like more or less a good kernel for identifying the hyperplane. I shall talk about kernels in the regression setting so that this idea will be clear over there. Even though it is done, you can see your cost was 5, 1 observation. So 2 observations are misclassified over here. Okay, so they are misclassified, and you can see over here something like that. Okay, you can see misclassified. Which are those 2 observations? You can see this is an observation from class 1 which is misclassified. This is an observation from class -1. Sorry, from -1. It is misclassified. How do you verify? You see the color. Red color observation, red color crosses are from class 1, and black color crosses are from class -1. Okay, so these are correctly classified, whereas these two are wrongly classified, and so on. Okay, so these are the references for uh, classification part. You can see, particularly one can refer to this guns tutorial. This is very fantastic technical report, and if one is really interested in the mathematics behind support vector machines, one can see this. And if you just want to understand what exactly the method does, you can just refer to Chatham Valley. And even, of course, this has both mathematics as well as explanation. And this is a little bit complicated, but you can understand after one or two readings. So this was all about classification. And now I shall switch on to regression part. Yeah, I guess I have still 20 minutes. So let us talk about regression using support vector machines. Okay, so regression formulation is little bit different. Little bit different in the sense like margin is, the concept of margin is same. Only thing is that you don't have y to be either -1 or 1, but it is kind of a continuous variable, a real valued variable. It will take values from a set of real numbers. So there will be no like threshold or something, but we shall have something like a predicted value which will be coming out of this particular setup. You can properly scale depending on, like in case of neural network as also, and in case of support vector machines also, usually people scale the data. Scaling is done using different functions. Scale data is used as an input. There are several reasons for this. Reasons like from optimization purpose also. If we are having like scaled data, scaling is done using like some proper metric, then usually the optimization problem, whenever you compute some Hessian matrix, which is whose inverse is required in several places, that Hessian matrix, if it is close to singular, that inverse cannot be computed properly, and thereby optimization problem cannot be
Sir,
solved. Yes.
sir, sorry, one person is presenting the Mohan Bharathi.
Okay.
Please remove stop your presenting. Mohan Bharathi. Already he posted the chat box, sir. He continue the Mohan Bharathi.
Okay. Okay.
So I removed, sir.
Okay.
Okay, sir.
I am
Let's
stopping, and I am again. Yeah, I am again continuing.
continue, sir.
Yes. Yes. When did this happen? Now only or earlier?
Is few minutes is there.
Oh,
Already posted message, sir. He not forgot it. Then again telling that.
okay. No, otherwise my slides wouldn't be visible to them. I will be just
It no
talking.
only
So,
presenting, sir. Early is
okay,
hidden, sir.
okay,
Mm.
okay. No problem. No
Okay, sir.
problem. Okay, now it's just 20 minutes left. I guess let me talk about regression and support vector machines. So as I was talking about, like there is a difference in classification and regression. Similarity is like we are predicting. A difference is what we are predicting, that entity is different. Here we are predicting a real number rather than a class label. So already we have seen this setup. Only thing which I shall require is that this particular aspect. Okay, let me use this pointer over here. So this is actually one important process in this entire setting, like why we need support vector machines, or even artificial neural networks. See, in linear regression, we assume that the relationship is linear, and we assume this model, we fit the model with such assumptions, and then again verify whether assumptions are valid or not, and then if everything is fine, if model is fitting good, then we proceed with the prediction. In practice, this x beta, meaning y is equals to x beta, may not be a good approximation in many cases, or these assumptions may not be valid for certain data sets. So what it means is that there may be some function which is relating y and x in a different way. That function is actually nothing but f. Fortunately, if you know the function from the domain knowledge, and if it is not linear, you can still do parametric regression using your nonlinear regression techniques. But if unfortunately the form of f is not known, then the only alternative left with you is to assume that only there is some relationship between y and x. You don't know the form of relationship. You try to predict y using the data. How do you predict? So you can go for non-parametric regression techniques, or you can go for this machine learning techniques. So non-parametric regression techniques, you will see kernel regression is there, lowest regression is there, and there are so many other approaches, rank regression and so on. They are there, which are actually trying to predict y when the function relating y and x itself is not known. And a data-driven approach is something like either you go for artificial neural network or you go for support vector machine. So here we are actually going to see, like, when f is unknown, how one can predict. We shall start with the linearity setup so that the concept will be clear, and then we shall make it non-linear and unknown. Okay. So already we have talked about this. Yeah. So let us have a data of the form x1, y1. Now this x1 is actually a vector. Okay. The first vector you can see like on p variables. So x1 is the first data point corresponding to which the response value is y1. So this is kind of a tuple. Okay. So these are tuples, n tuples we are having. And we first assume, or rather we shall first write that f is linear. Let us go with first linear, and then we shall see when the relationship is not linear. So first we shall assume that the relationship is linear and see how this can be trained. Okay, and when it is non-linear and not known, then how the problem can be modified. So we want to find the best function to predict yi for given xi, and the function is actually assumed to be a linear, like w transpose x plus p. So in general regression problem, we need to find w which minimizes a loss function. Usually the loss function is your least squares, something like if you call your yi as the observation and f of xw, so let me put it as w hat transpose x plus b, okay, xi for example, ith data point, its square summed over I running from 1 to n. This is actually nothing but your sum of squares of errors or residuals. This is called as square. So we minimize this as a function of w to find least squares estimate. Inside quantity can be treated as loss. So there are several ways of expressing loss functions. You can see this is your quadratic loss, the one which leads to least squares estimate of w. Okay, this is Laplace, which leads to least absolute deviation estimate of w. Hoover, you might have seen this in the in your earlier special lecture, I guess, wherein outliers were treated. Hoover is actually a loss function used to estimate parameters in the presence of outliers. This gives rise to popularly called Hoover's M estimator and its variants. You can have like M estimator, that is two-stage M estimator, and so on, or even GM estimator, which is actually an estimator from the class of like Malu's class of estimators, which are robust to presence of both X space as well as Y space outliers. So you can see like from a different angles, like Huber's laws can also be used. The loss which we are going to talk about today in support vector machines is this one, epsilon insensitive. This epsilon insensitive loss is actually a modification of Laplace loss. You can see it is very closely related, but it is little bit modified. The idea will be clear from the next slide, wherein I shall be showing you the pictures of these loss functions. So this is your quadratic loss or the least squares loss, which is a nice concave convex function. This is a nice convex function. This is also a very nice convex function with the problem at this particular point, wherein it is not differentiable at this particular point, and therefore usual calculus cannot be applied, and it becomes like a problem to be solved. It becomes a difficult problem to be solved in the application purpose. And Huber, you can see Huber, you might be wondering, sir, how it is different from this and this. Yes, it is different. You can see up to certain level it is behaving like a quadratic function. Okay, so in this zone you can see, in this zone it is a quadratic function. Beyond that zone it is Laplace. So you can just say combination of these two becomes a Huber special combination. It is actually removing the I should say non-differentiability of Laplace using some function which is a part of this particular quadratic function. At the same time, the tapering ends, the tail ends, they are actually borrowed from the Laplace, something like that. So that you can see combination of Laplace and quadratic becomes your Huber. And epsilon insensitive is like one step ahead. It doesn't bother about this particular zone. It just cuts off and it makes the error exactly zero if your deviation of the observed yi and predicted yi is less than some epsilon in absolute. If that is happening, the error is actually treated, or the loss is actually treated as zero. Otherwise, it is growing linearly. Okay, it is growing linearly. You can see over here the more detailed picture of epsilon insensitive loss, which was introduced by Vapnik, the Vladimir Vapnik, in 1995. He is the one who actually proposed support vector machine, the idea of support vector machine. So he actually started with classification. Later on, he gave, I should say, or rather extended the support vector classification technique to support vector regression. You can see on x-axis value of the target is there. On y-axis there is penalty or loss, you can say. If you can see if your error, or you can say deviation, is less than epsilon, the loss is zero. So you are tolerating loss in this zone. You don't bother about points which are falling or which are having error, or you can say deviations less than epsilon in absolute. For other points, you are not going to tolerate. So these are the points, meaning these are the losses which are actually incurred when the deviations are greater than epsilon. So let us try to see like what exactly this this loss function tells. So if the value of the estimate f of x of y is off target by epsilon or less, then there is no loss. That's what I said. If the opposite is true, then the value of the loss function rises linearly. Okay, and the goal is to find f of x that has at most epsilon deviation from the actual obtained targets for all training data, and at the same time as flat as possible. So this is an important thing, so that your objective function will be coming according to this particular goal. In other words, regression algorithm does not care about errors as long as they are less than epsilon, but will not accept any deviation larger than epsilon. So that is an important thing. You can see in case of simple linear regression, this is the tube, I should say. This is an epsilon insensitive tube. From here to here, this is called as, okay, let me put it like this, epsilon insensitive tube. That means if for this point, you can see, for this point, error is this much only, which is lesser than epsilon. For this point also error is lesser. So these points are not actually bothered because for them error is less than epsilon. So only those points which are having error greater than epsilon, they are targeted. And you can see the equations over here. You can see equation for this is y is equals to xi wi plus b. For this is xi, you can see yi minus, you can see over here yi minus xi wi plus b is greater than epsilon. And over here you can see like xi wi plus b minus y is greater than epsilon. You can write it the other way around so that it will become less than epsilon if you want to put it in this way. But that is fine. You can write it in the positive part in both the cases. So these are the distances you can see, or you can say the equations of these planes. Okay, this is another hyperplane. You can say again the supporting hyperplanes, and these are the points which are close to these hyperplanes. They are again called as support vectors. So again, finding this line is actually nothing but first find the support vectors and then do these points which are falling in this epsilon insensitive tube. They are not used for the purpose of building the regression model. This is exactly opposite in case of your classification. In classification, we don't want anything to fall in between because that was the region of like ambiguity. Here, that is no region of ambiguity, that is the region of like accuracy. Here, if you have the points falling in this zone, that is epsilon insensitive tube, you can say that the points are actually having error which is pretty tolerable by the system. Only those points whose error cannot be tolerated, they will be thought of, and then a line will be learned, or a plane will be, hyperplane will be learned by focusing on their contribution of these points towards this line. You can see in case of linear, this is how it is happening. Okay, and in case of non-linear, you can see this is the thing. So that I was telling that in case of non-linear, this will be kind of a function which will be learned from the data. A similar kind of a classifier also will be learned. I didn't put this purposefully in the classification, but you can see this is also possible in case of classification, except these points will not be there inside, they will be outside. So on this side one class, on this side other class, something like that. But in case of regression, those points which are falling in between, they are actually forming what is called as an epsilon insensitive tube. Okay, in case of linear, here it may not be a exactly tube, but it may be something like a bend tube. Okay, in a very random fashion. Again, you can see the error over here, like you are seeing that this point is much far away from this. This is actually again treated as xi. Okay, meaning the distance from this point to the hyperplane is treated as xi, and this is also xi. You can accordingly denote these values over there. I shall explain those things in the optimization problem. So let us consider this linear regression model, which already we started with. And of course, the goal of regression algorithm is to fit a flat function to the data points. Okay, so flatness in the case means that one seeks a small w. We want value of w to be as small as possible. That's what essentially we, and one way to ensure this flatness is to minimize the norm of w. Okay, it's a square. That is nothing but w transpose w. This is simply w transpose w, which we are already having over here. So objective function is still the same. You either minimize w transpose w or you minimize half of the w transpose w. It is same because only half is coming over there, which is like a scale invariant. The complete problem is scale invariant, and thereby even if you multiply by half doesn't matter. This half actually takes care of the derivative of this particular thing, when of course you can see like how it will vanish. Fine. So now you can see yi minus. So these are the conditions. You can see here the conditions are changed. You can see yi minus xi prime w plus b is less than or equals to epsilon, and this is like xi prime w plus b minus yi is less than or equals to epsilon. These are the conditions on the objective function which we are actually minimizing in case of support vector regression. And if we are having like some errors, then we have to introduce some slack variables like Xia and Xia star, which I was talking about. Like if we are having points far away from these lines, then we need to put some trade-off for them. We need to put cost of including them into the setup, and thereby the cost associated with these points which are far away from this will be less, okay, meaning high. It will be high, so that their contribution towards the model will be less, and so on. Just like outliers, if you remember M estimator is an estimator which assigns weights to all the observations. In case of linear regression, if you are having an outlier, outlier will be given very less weight, whereas the other observations which are like called as inliers, they will be given weight very close to 1, and accordingly the weighted least squares estimator will be computed. Weight function can be Hoover function, meaning weights can be obtained using Hoover function. So accordingly it becomes like Hoover's M estimate, and you can see that the effect of outlier is nullified. It is kept as less as possible because it influences the key model properties when it is not treated specially. Similarly, over here also, these points are going to create trouble, and thereby one needs to see that their prediction is also they are not going to create trouble for like predicting other observations, and thereby they should be penalized in a proper way. So again you can see like they are penalized using the introduction of slack variables into the problem, and it becomes something like, again with cost factor, you can see cost Xia from one side, Xia star from the other side, and accordingly your problem changes. So again hard margin becomes soft on the either sides, and thereby this also tackles your nonlinear case. So this is actually doing both, handling nonlinear case as well as the linear case. Now let us talk about like when you have actually nonlinear setup, how one can actually do this particular thing. So before that, let me just finish off this particular thing, like how do we solve this problem. Again, the solution is based on the method of Lagrange's undetermined multipliers. This is again a convex problem, and its dual can be solved easily using any quadratic optimization tool. Yeah, you can see over here the Hessian, the Lagrangian function and the Lagrangian multipliers and so on. Okay, so I shall come back to this C and epsilon. Before that, let me just focus on this non-linearly separable case. See, whenever we are having a non-linearly separable case in classification or non-linear relationship in case of regression, this non-linearity can be handled very effectively using what is called as kernel trick. This kernel trick is actually something like you are projecting the low dimensional data into high dimension. Usually we do one thing, we rather reduce the dimension, but here we are not doing that, we are increasing the dimension. I am again going back to the classification setup wherein the data may not be linearly separable. In that case, what you do is, if the data is not linearly separable in say variables x1, x2 and x3, then whose dimension is say 3, then you can transform this data to a higher dimensional space. Something like, okay, if you are having this as your input space, you can transform this to what is called as a higher dimensional space. Okay, you can transform this to higher dimensional space, which can be resulting into a single output. So if data is not linearly separable in a lower dimension space, you can simplify, or rather you can zoom out your lower dimensional space into an higher dimensional space, so that data will be linearly separable in a higher dimensional space. So how it can be done? It can be done by raising the dimension, by substituting x1, x2, x3 by some function of x1, x2, x3, some phi1 x, or you can say phi I x. You can put I is equals to say 1, 2, 3, up to 6. For example, this can be converted up to 6 dimensions. You can go beyond this also, but sometimes 6, you can stop at some particular point. You can make it 6 or 5 or whatever you feel. So you can go for like some, okay, let me put in general, say k, where k is definitely greater than 3. Okay, in general. So you can have like replaced phi xi's in this particular pattern. For example, your phi1 x may be simply x1, or I can just say phi I x is xi for I is equals to 1, 2, and 3. And for remaining, say phi4 x, let me put it as say x1 square, phi5 x, let me put it as x1, x2, and phi6 x, let me put it as x1, x3. What I have done is I have replaced x1, x2, x3 by polynomial of degree 2 in x1, x2, and x3, and thereby the feature space is now having dimension higher than the input space, and therefore the data which is not linearly separable in this may be linearly separable in an higher dimensional space. But the problem is, if we go in higher dimensional space, we always need to work out the dot products w dot x. In higher dimensional space, computing this will be more tedious. That is particularly called as curse of dimensionality, and that can be tackled by using kernel trick. So yeah, I'm coming at the end of the presentation. So this that can be tackled by kernel. Okay, that can be tackled by
Madam, mute, madam. Continue, sir.
yeah. So that can be tackled by kernel function. The kernel these phi's are actually functions which are called as kernel functions. One need not worry like what the form of the function they are choosing. You can choose any type of kernel function. Accordingly, the kernel functions will also have some user defined constants, and you have to tune your setup using your knowledge and your expertise in the field, and you have to set the values of user defined parameters in a proper way, which can be justified for the reasons outside data. Okay, and thereby you can work out, like instead of finding these functions, you can just use a kernel function. Like there is a linear kernel, there is a polynomial kernel. This whatever I wrote is an example of a polynomial kernel, and so on. There is a Gaussian kernel, exponential kernel, exponential Gaussian kernel, and so on. Even there is a perceptron kernel, and so on. Even perceptron can be used as a kernel, like exploring the same data, rather projecting the same data into higher dimension. Usually we do it the other way around. To understand the setting, we reduce the dimension so that handling of the data becomes easy. Here it is the other way around. Here we are actually making data to go into an higher dimensional space. So this trick is actually fantastic, and what happens is the data which is not linearly separable in lower dimension becomes linearly separable in higher dimensions. A classifier can be constructed over here with the help of kernel functions. You don't need to work out all the computations in the feature space, which is of higher dimension. You can do the computations in the lower dimension itself, but construct a classifier in the higher dimension which linearly separates your data, so that the nonlinear separable case plus curse of dimensionality can be tackled with the help of this magic wand called as kernel functions. Okay, the same trick is used in case of nonlinear regression as well, and this kernel function will be actually appearing in the objective function of your optimization problem. Instead of like W transpose X, you will have kernel function of W and X. That's it, nothing big. Kernel function in the form of W into X, the dot product. nothing different than that. So that is, if we are using like kernel function as it is, then the multiplier is actually nothing but zero point 0.5. That 0.5 is by default, that is 1 by 2. 1 by 2 is actually nothing but the multiplier over there. So that is actually linear kernel. Linear kernel is of no use. It is as good as writing your objective function which is already there in the setup. So linear kernel should be replaced by either you can go for polynomial or Gaussian, or you can go for exponential Gaussian or perceptron, or there are even so many functions, kernel functions which can be used over there. Same trick can be applied in case of regression, and nonlinear regression can be implemented. Okay, coming back to the presentation. Yeah. So now here there are two values. One is value of C, that is the trade-off between model complexity and the degree to which deviations larger than epsilon are tolerated in optimization problem. And also we need to choose epsilon. So for choosing C, you can see like many methods are available. I will show you on the next slide how one can choose C, so that you can tune in your classifier or your regression setup. So see here we are actually talking about regression. So if C is too large, then the objective is to minimize the risk only. But if C is very small, then you are actually making like error of all the observations to be, almost all the observations to be non-tolerable, and you are still learning. So it is something like going towards your least squares estimation. Okay. Parameter epsilon controls the width of the epsilon in sensitive zone used to fit the training data. And if you increase the value of epsilon, more error will be tolerable. And in this case, you may have trouble to get good accuracy. But you cannot make even epsilon to be exact 0. That may happen when you make your C to be like very small. Okay, and in that case, you can see like both C and epsilon affect your model complexity in a different way. Usually epsilon is taken so that 50% of the data points are uh, uh, are treated as support vectors. And for C, you can see over here on the screen, yeah, I can tell you like parameter C and epsilon are selected by prior knowledge and our user expertise. Choose epsilon so that around 50% of the samples will be support vector. This was actually suggested by Matera and Haken in 1999. And epsilon is actually suggested to be chosen as proportional to noise variance, and this was given by Schmoll and others, and Koch. And these are two choices for C only. C can either be taken as range of output values. Range is like max minus min. For this was given by Matter and Haken, and this is given by Cherkassky and Ma. This yes is actually a notation for C only. So C can be chosen chosen to be equal to yes as maximum of absolute of y bar plus 3 sigma y. This is kind of like 3 sigma limits which usually appear in your statistical quality control, but in the absolute terms they are maximum. This value is actually taken as of course there is no much theoretical justification available for these values. These are like values which are producing reasonably good support classifiers. Essentially everything revolves around selecting the values of C and epsilon through prior knowledge and or expertise. These are the references. Yeah. So that is all from my side. Let me thank once again the organizers for giving me an opportunity to talk, and also the audience for patient listening. And thank you one and all. Over to you, sir. If there are any questions, you can ask.
Yes, participants, please free discuss with any query, doubts, depends upon defense. Discuss with sir. No more question? Sir is
Oh
taking
my.
2 sessions. No more questions.
Any you can ask from the first session also, no problem. If you have any doubt in first session, you can clarify it right now.
So I think chat box one person is.
Yeah, I'm looking in the chat box.
Yes, sir.
Uh, there is no question as such. Yeah. So thank you once again. If there are no questions, I guess then we can stop.
Okay, sir. So formally, thanks to uh, today's very wonderful sessions. Nice
Now there
explanation,
is
departure.
there is one question. Let me. Sorry to
Yeah.
interrupt you. Uh, yeah. This is from R.A. Gadekar. Which type of data set required for SVM? Data sets, see, it depends on like what task you are doing. If you are doing classification, then data can be in the form of your classes, labels, and some predictors x1, x2, xk. I showed you like sample data earlier also. It can also be in the form of image, but image needed to be converted in the form of numbers. That conversion can be done either using MATLAB or even SAS or any other software like Python. Python nowadays people are using uh, recognizing patterns in images. So data is it can be of any form, but it needs to be converted into a proper format, which can be given as an input to the support vector machine. And the proper format is nothing but numbers. So
நீங்கள் ஃபுல்லு
ultimately,
தானே இருந்தீங்கம்மா வெளியே வரல இல்லைங்க
yeah, so ultimately it will be in the form of numbers, and only class label. If you are in classification setup, then class labels will be there as a response. If you are in regression setup, then it will be real numbers on the response. I hope it answers your question. Yeah. Yes, sir. You can proceed.
Any more questions? Otherwise, I to formal vote of thanks propose
Yeah.
myself. Yeah, thank you very much, sir. And also, uh, I when I called them, I immediately accept my invitation, sir. Thank you for your kind cooperations. And
Thank you. Thank you for giving me an opportunity to be with you all.
yes, sir. Yes, sir. Thank you, sir. Thank you very much. Once
Thank you.
again, thanks to Dr. Sheikh, Assistant Associate Professor, Department of Statistics and Applied Mathematics, Central University of Tamil Nadu. Sorry, both of sessions given the two titles, classification and prediction using artificial neural network, and the second session of title is classification and predictions using super vector machines. The based on associated with how to communicate, how to develop the base become from equations. So very nice, wonderful sessions. And thank you once again. Thank you, sir, for
Thank you.
your spending with the time and the schedule of busy schedules today. Thank you very much, sir.
Okay. Thank you. Thank you very
Thank
much.
you,
Bye bye.
thank you,
Have a nice day.
thank you, sir. Thank you very much, sir.
Okay. I'm leaving now. Fine, no?
Okay, sir. Okay, sir. Thank you,
Okay.
sir.
Okay. Bye bye.
Bye, sir. See you, sir.
See you. See you.
என்னங்கம்மா எதுவும் இல்லை எதுவும் பண்ணாதீங்கம்மா இருங்க லேப்டாப் கொண்டு வாங்க ஹலோ ஹலோ Sir, participants, any question? போயிட்டு தான் இருக்காங்க. மைக் ஆனில் இருக்குங்களா?